Well, welcome to our structural modeling video conference for April 2018. We're going to be covering some interesting but very kind of basic ideas of system concepts and theories. He kind of builds on a theme that we've been working on and started the last couple of months of looking at system theories, system concepts, specific one theories, general theories, how they're the same, how they're different, what are proper uses of mathematics and mathematical techniques, where they might be properly applied, where human observation plays key roles, things like that. So, and we're in the process of building toward the next couple of reports, which will go into this these in a little more detail from a historic perspective and look at things that people have done in the past to make sure that there's a proper alignment between the mathematical functions and the substantive empirical data. So with that, I think I'll just kind of start walking through the read ahead here, because we're talking about system theories and system concepts as they're used in structural modeling and structural integration context. We'll define key terms, processes, and concepts, and discuss the basic scientific process, those steps in the structural modeling components and activities. So one of the more interesting things about a system concept is that we really need to look at the two parts of that. First, the system part, and then the other part, of course, is the idea of the concept itself. So we'll look at the two definitions of a system. One which is a construction rule, and the other is a functional definition of a system. Of course, a functional definition of a system is a constraint on variation. So in the observing behavior of something, you see that it has a constrained type of behavior, a constrained pattern. You infer that there is some type of system or something that is constraining those objects to behave in that constrained manner. And of course, the example here is Kepler's discovery of the laws of planetary motion. The human beings had observed the motion of the planets for a long time. There have been many different mathematical theories proposed to define the system. Kepler came up with, during his time, the most accepted theory and description of the solar system and how the planets move. That was based on the constraint of the planets themselves. So that's kind of a functional definition of a system. And then the construction rule kind of have two different definitions of a construction rule. One form is that the system is a relation mapped over a set of objects. So this is a fairly straightforward definition that we've been using for a while, but it has some problems with the more formal mathematical terms in the definition itself. It's a natural language statement, and we've included some mathematical terms like set and relation map. And by doing this, then what happens is there are some ambiguities and misunderstandings are injected or could be injected into the definition because of the use of these terms. And so, of course, the terms would be associated with a mathematical set doesn't allow any duplicates. And of course, every mathematical set has an empty set as a subset. So these kind of things can become confusing. So we've created another similar form of the construction rule, which is a system is a relationship associated with a collection of objects. So in this case, we've gone from the term relation map to relationship associated with. And so we've always used a relation to mean a mathematical relation, and we always use relationship to mean a natural language type of relationship. And then associated with, it's a little more flexibility than the more formal term mapped, and with a collection of objects. And it's my understanding that Counter and some of the folks that started with working with set theory, they actually started out with the idea of a collection of real world objects. So we're kind of stepping back and saying, well, okay, we're going to be dealing with a collection. Now, a collection is less formally defined than a set, and that allows us to introduce some ambiguity, but also allows us to use natural language contextual statements to address and eliminate that ambiguity in the process. So we can use either one of these definitions. The idea is to pick the one that most clearly communicates your purpose in context, in whatever context you're working in.
So is this a Simpson set of definitions? And would you elaborate a little bit on the concept?
So the construction rule is our definition. The functional definition is from a fellow at the Free University in Brussels. Halligan, I think is his name. And they have, he also has a definition for a metasystem where a metasystem is a constraint on variability. And so he's done a lot of work from looking at more of a functional type of approach. But because we're focusing more right now on the structural type of modeling of a system, we have tended to focus on the construction rules, and then those are the ones that we've basically come up with over a period of time. That makes sense?
Yep, thanks for that.
So, okay, so anyway, it's clear that the concept of a system includes arrangements of object as well as the behavior. But as I said, we're going to be focusing now just on the structural part here and not really focusing on the functional behavior yet. That'll be something that we'll address later on as we more further develop our tools. So conceptual frameworks. So, you know, again, observations and concepts make little sense if they're isolated. And so we have basic networks and collections of concepts are basically called a theory. We have, this is from Hall 89. We've adapted this particular approach to the scientific process. What you can see is a theory is some kind of interconnection of concepts. So based on some of the information that we've done before, we've done previously in the last couple of technical reports, we say that if this is a mathematical theory, then almost all of these concepts would be mathematical concepts. And if this is a specific systems theory, then these concepts could be mathematical, they could be general system concepts, and they could be specific system concepts associated with the specialty system. So you can have different types, you know, and a conglomeration of different kinds of system concepts in a specialty system theory. In a general systems theory, here we would only expect to find general system theory concepts and mathematical concepts. And it's one of the areas that we will, again, continue to refine this and continue to make a discrimination between these types of ideas. But what happens is in the natural, informal realm, factual realm, we take data and observations, cast them into a formal modeled theory. And then the advantage of that in the formal domain, we're able to use deduction for prediction. And we'll then use that as a calculation and then confirm or verify. Then we look at what are the implications of the predictions, observe, take more data, and confirm or verify that it's either true or not true. Compare and go again. Now, the induction, which goes from the general to the specific, is interesting because it's a similar definition to a concept. Concept is something that's kind of abstracted from general observation. So it's kind of the scientific theory, that the scientific process, approach that sets the context of what we're talking about. The key aspect here is that the theory is just a network of concepts. And a discriminator that we've made is that we will now be able to say that a mathematical theory would only have mathematical concepts. General systems theory would have mathematical concepts and general system concepts. And a specific systems theory would have mathematical concepts, general system concepts, and also the specific system theory concepts involved. So we can now start looking at the different types of concepts that are in the theory to start a categorization process. Okay. The Clear theory is based on a collection of interrelated concepts, right? So that that's clear where the generation of the concepts take place. And so this is, again, another interesting area that, especially in systems, that needs to be thought about and determine where we can leverage these processes to get the most benefit from them in our data collection and generation. But inference reduces uncertainty and develops a clear, objective views of the world. Abduction generates theories, conjectures, hypotheses. So this is where hypotheses come from. Abduction, explanations not yet verified by induction or deduction. Then induction generates conclusions based on observations of experimental data. And deduction is a process of formal mathematical reasoning that produces a conclusion based on a set of assumptions given as true. So in a short quote here from some of Percy's work, is every perceptual judgment shades into an abductive inference or hypothesis, and further elucidation of the meaning must involve phases corresponding to deduction and induction. So I think the main interest here for systems scientists, systems engineers, systems practitioners, systems researchers is the fact that what we need to do is apply our tools in the area where they're the most appropriate. And so the perceptual judgment is going to have human abductive type of reasoning. So the human intellect has got to be involved in it somewhere. But deduction allows us to actually, which is included in deduction, that's a mathematical process. So we can kind of hand that off to a machine. If we have very large scale types of rule sets or large scale information systems, we can now, and if it's put into a formal rule set or formal theory, then we can hand the validation of data off to or an observations off to a machine. Induction, however, we can do that. I think there's a process there where we can augment human intelligence or human understanding with computers and machine intelligence by large-scale search in environment and in evolutionary programming and evolutionary computation. So there's really different types of computing support tools that can be used in each of these different phases. They can be integrated and they can be leveraged in a way I believe it can have a lot of benefit. Okay. Again, I said it's interesting to note only theories cast into a formal format may be located in the formal realm. And that's the formal, it's going from the informal to the formal, which is interesting because at first when you have a theory, it's informal, you cast it in a formal format, then you test it to see whether or not it holds. And so there's that type of process of refinement and testing and verification and validation. And of course, it can always change. You always have some new information that completely discounts or shows that your theory is wrong. But the most basic level, a theory is just a well-defined structure of interrelated concepts. And you need to first, basically identify the concepts. And then the second activity is structuring these identified concepts. The first activity of concept identification for theories, we said, okay, we're now starting to categorize the theories a little bit by what kind of concepts do they contain. And so we can now start to develop a graded range of theories, and the graded range of theories will be placed on that range or on that scale somewhere because of the types of concepts that make up the theory. And so that is a metric that should be used when we're talking about and just basically aligning conceptual theories. The second activity, of course, is structuring these identified concepts. So how do these concepts align with each other? They're important things to note, but not quite sure. These are things that really need to be addressed, and there's many different attributes and characteristics, not only the concepts, but also the theories that can be used to distinguish them from each other. And so one of the things about the theory of interest, it's an aggregation of system concepts. And so when we're looking at a system concept, it can be two different forms. It can be either an atomic concept or a composite concept. An atomic concept is not separable into other concepts. And a composite concept is separable into a collection of other concepts. So this becomes interesting from a theory construction point of view, and it becomes interesting from a theory identification, the categorization point of view, because it depends upon how far down into the scientific details you want to drill in your concepts. We think this goes back a little bit to the sciences of the artificial, where they talk about the different levels of scientific inquiry, and that Newtonian physics itself was done at a certain level. And it didn't dive down into the atomic particles or subatomic particles, the quarks and types of an action at a distance and all those types of physical phenomena that happen at much different scales. So those two things are going on at different scales, And quantum physics did not negate Newtonian physics. You can still, at the scale of Newtonian physics, you can still work with things that are concepts that are about, you know, velocity, and concepts about weight, and concepts about mass. Quantum physics didn't eliminate that. So the idea here is what level of observation and what general level of inquiry or what general level of engagement are we going to freeze our atomic concepts? So in Newtonian physics, we stop at the atomic level and molecular level. We don't go into subatomic particles. So these are some of the things that will need to be addressed, and we'll need to come up with some type of framework within the systems sphere to say, okay, these types of systems, we can freeze our concepts at this level and they can be atomic. Other types of systems are composite, and we're going to need to have to drill down into those or recursively or whatever to clearly track and identify the current concept known. So this is just something that needs to be addressed kind of on a different level.
Yeah, and how would you actually make... Whoa, sorry. There's a lot. It would be good to devise a way of determining the approach to the concept description by level of complexity or level of concreteness or level of abstractness.
Yeah, I think it's Herbert Simon, I think, that did the Sciences of the Artificial. I think he came up with a hierarchy, and he did some work that kind of would be a good, I think, is kind of a starting place for that, what you're talking about. But it's exactly, yeah, that's, it's there's some people that have done that. It's kind of disconnected. Warfield did it a little bit. Simon did it. Can't think of the other one or two people right off the top of my head, but yes, there has been work done in that area.
Yeah, it would be just interesting to map it out. And 20 years ago, I was working with theories of organizational complexity and leadership capability that's matched to that complexity. And we looked at, you know, concept organization at different levels of an actual organization, and also of cognitive capacity and capability. Anyway, that's just what comes to mind thinking about this.
Yeah, and I think there's some very we can start with some very simple types of examples and then use those as kind of canonical conceptual benchmarks. But one of them would be the idea of like a recursive concept, right? Like addition, you know, 1 n plus 1, right? N plus 1 can go on forever. That's a very simple recursive concept, but it generates an extremely complex system, right? And so one of the ideas here, of course, is the atomic concept as opposed to the composite. The composite concept, if it's generative, has some very interesting benefits. And one of the types of recursive concepts that Warfield used was the propagating relationship, transitivity. So that if you have these aspects of your system that are okay, so we have someone trying to call in here, and I simply don't have the when I'm in broadcast mode, I can't see what's going on and see what's going on here. So give me just a second to go ahead and try to do that. Okay. Okay. All right. So I think I've been able to address that. So where were we? Okay, so we're talking about the two different forms, the atomic concept and then the recursive or composite concept. And an example of the recursive type of rule set for numbers is just addition, which generates an infinite stream of values, which is very complex. And then the other part, of course, is the idea of a generative type of logical property like transitivity, which, hello, Kevin, that brings that together and makes it work. So these are the types of attributes that we can actually.
Welcome, Kevin.
Hi.
These are the types of attributes that we can now associate with the concepts in the system. And as we go forward and try to identify different types of theories based on concepts, now we're assigning attributes to these concepts that will allow us to further categorize and generate different types of concepts. So, Kevin, have you been listening, or did you just log in? Would you like us to go back and start anywhere else, or what would you like to do?
Just give me a recap.
Okay. Well, what we did was we just went through and talked about the basic scientific theory, the system Hall, and that system concepts make up system theories. The concepts are a network of theories. We talked about different kinds of theories are composed of different kinds of concepts. And so we talked about generating classes of theories, and then we're talking now about concepts and attributes and characteristics of concepts that would be useful in the categorization process. And then what we want to do, of course, is figure out between the informal, natural realm of discussion and the formal realm. Formal realm, we can use computational machinery to help. And then in the informal realm, we might be able to use computational machinery to help in certain areas. And then in the crossover, going from the informal to the formal, are the areas there where computational machinery can help. And then going from the formal to the informal again. How can we augment human intelligence with computational machinery? And then let's see, we talked about inference, adduction, induction, and deduction, how these work together. And we were talking about concept identification and then structuring the identified concepts, structuring them by either an atomic concept or a composite concept. And then these are attributes of a concept, of course. And then we were talking about how essentially we could use those in further classifying theories and concepts. And it's possible to explore common types of behaviors associated across a wide range of systems. And of course, in this document, we do not address this type of behavior commonality because we're focused on structural modeling right now and developing a set of tools to address system structure. But what we will do in the future, the plan, is to then bring that in and start exploring the connection between system structure and system behavior. And then hypothesis generation. So part of the scientific process, of course, is generate a hypothesis, and theory testing and validation is based on hypothesis generation and testing. And so quality of existing data, adequate amount of data with low probability of measurement error. We talked about the Kepler and doing the solar system as an example of the constraint on variation in the functional theory. Kepler knew that the data he was working with had low measurement error. He'd been up the Tycho Brahe's area. He observed them taking the measurements. He knew that they were very careful. So he had adequate amount of data with a low probability of measurement error to work from. This is really important when you're talking about verification of theories and data, and these concepts need to be carefully evaluated. So essentially, once you have a good enough data set to support your activity, you basically, you're going to, the people that are in charge of the research are going to revise the hypothesis and select the variables and attributes that are needed in the testing and validation phase. And the variable selection should focus on statistical power and resource minimization. So one of the key things here to think about is what are the variables we're going to select when we're talking about and looking at system structure and system behavior, and how are we going to separate these concepts from the relationship. I was telling Peter a little bit earlier, and as an introduction to this particular report, so this is a precursor to the report next month, where we're going to address Robert C. Tyron's cluster analysis and talk about his work with psychological data with human subjects. He also worked with rats, he worked with animals. But what he did was he developed a type of data analysis approach that he used as an expert. So he proposed his theories, he designed his experiments, he did his hypotheses, he took his data, he generated the variables for measurement, and then he did the starting back in the 30s when all the calculators were hand calculators. And so he did all the calculation and verification of his data by hand. So one person spanned the whole space. He knew the mathematics of the verification, he knew the theory and the specialty theory, and he basically grouped them together. Over a long period of time, he developed and became a known expert in cluster analysis. And one of the things that he did was, and in his work, and we're going to talk about next month, is a variable selection. In his case, when he was selecting variables for analysis, he would only select variables that would order or impose an order on the subjects. And so he not only took the data, but in his variables that he selected for his testing, he wanted to have the aspects of his subjects of study. He wanted to be measuring and taking data on things that would allow him to place those individuals in some kind of order, whether it was how fast they could run or how tall they were, how much they weighed. These things could all place all the subjects. They were global types of variables that could impose an order over all of the subjects. Because of that, then he also used logic. He used logic much more to reduce the computational type of burden because, as I said, back in those days, a lot of the stuff was just done by hand. So it's what we'll be doing as we go forward, we'll be looking at the ideas of variable selection, which ones, what variables, what characteristics of the system do we really want to test and measure. And to start that process, we will look at the work that Chiron did, and also some of the work that Warfield did, and some of the work that Hartigan did. So in this area. So, system theory testing, we may benefit from focusing on only one type of system attribute at a time. In this particular case, we're working on the system structure and focus on identifying these types of general system attributes, patterns, and interactions. So we really want to look at and pick these things, variables for testing that we can use that allow us to leverage logic and allow us to order whatever the subject of our hypothesis is. So that's really a key factor. I was kind of surprised when I was going through reading this and discovered the fact that it's very similar to the published work with the GMU ISM software, where everything was in an order. And you could use logic to get there. I was reading then about Chiron, and he had many heated discussions with mathematicians about his approach, but he valued the human perspective and human intelligence understanding of the data and the application of logic to reach his goals more than just the mechanical crunching of numbers. And he developed types of statistical approaches that were that supported human understanding. And we'll talk more about that next month. And so the major challenge, of course, in systems hypothesis testing is the identification and validation of relevant data. So what are we going to be able to measure? What's common, right? So one of the things about the system we're looking at, of course, is like we use the construction rule. We'll say that a system is a relationship associated with a collection of objects. And then one of those associations we can talk about is a model exchange isomorphism. We've arranged the logical categories. We've got 27 buckets, different logical connections here. So we can use that as one of the attributes to say, well, what is the logical connection? So these are just some of the ideas that we'll be throwing out. We'll develop these as we go further. But system hypothesis generation validated testing is a key component of system science, and we need to be able to tell that story clearly. Say, have it clearly identified what the components are, what is the system, what are our hypotheses, what are our concepts, and how do they play together. And if we can standardize those basic activities, I think we'll have a better chance of moving system science forward. Okay, so specific system theories populate the literature of most professional scientific disciplines, right? So mathematical systems theories, of course, are in mathematics. General systems theories associated with structural integration modeling, and mathematical systems theories pervade all areas of structural modeling, basic structural modeling, and structural integration modeling, and interpretive structural modeling. The task of properly aligning mathematical theories with specific system theories encompasses the capability to generate data and information that support the creation of general systems theory. Specifically, Chiron in his work when the mathematics became so obtuse and smoothed the data and spread it out to where that the human researcher couldn't understand it, and it was no longer informing the human researcher about what was going on. He rejected those types of mathematical techniques, even though the mathematicians said they were sound and they were statistically okay and so forth. What he picked theories and mathematical proofs and mathematical techniques which were sound, but were designed to inform the human researcher so that the human researcher could grasp what was going on intuitively, get some insight. So these are the types of challenges I think that we have similarly in systems theories and systems hypothesis generation and experiment and testing, and saying, well, how are we going to inform the human researcher more than just spin the cycles on the CPU, right? Because you can generate data all day long, but no one knows what it means. So I think that's a key design criteria for this type of activity in system sciences. We're generating systems theories and trying to understand what the concepts are that support different kinds of systems theories, to understand and the differences between these two hypothesis testing techniques, choose the right kind of variables, choose the right kind of processes, and understand that there's different kinds, and that they have different outcomes, and basically are designed for different populations to ingest and understand. So again, mathematical deduction is an important part. We can have a direct type of support from computational machinery. Inductive reasoning can be augmented using computational machinery, but it depends, what kind do we want to use. Where does human intuition, where does human understanding become involved? So that's almost a design process, and I'm sure it's a graded range. But the act of creating a theory spans the space of factual and formal truth, mathematical formal truth. And that's really important, I believe, because there's a transition. What we're doing is we're actually transitioning our informal observations to formal concepts and formal statements that then now can have a computational capability. And here's just a little table that shows the scientific method operations, and it's so deduction produces a conclusion based on a set of assumptions given as true. They're not necessary, they may or may not be true, but they're assumed to be true through formal mathematical reason. And induction generates conclusions based on observations of the experimental data. And it can be based on a number of things. Truth value produces a formal true values for validation or verification. Every truth value output of a deductive argument is certain. You don't get, well, maybe or maybe not. It's either true or false. And induction does not necessarily produce true statements and outcomes. It's variable and probabilistic, and inductive arguments suggest truth, but do not ensure truth. So we're integrating these two processes with other processes in our systems theory development and in our scientific method. So we really need to understand how they impact each other. They obviously happen either concurrently or in sequence. It's probably better to look at them in a sequence. And so how do those impact our outcomes, what we're really looking for? Okay. So, as I talked about here, we need to decide where we're going to inject computational capabilities, and this is just a chart from Fogel, evolutionary computation. Unlike deductive reasoning, mostly what we have here can, of course, have deductive, but manipulation from the model hypothesis to the general solution. You can use evolutionary computational techniques to do extremely large-scale search looking for patterns. Mary and I have done quite a bit of publication in that area on how to identify clusters in the patterns, the manipulation for a general solution. And then deductive or specialization process in real world, there's a matching between the formalized process here in the real world, and that needs to have human observation. But instead of a human being have to look at 100 million different combinations, you can have a computational system generate, let's say, the top 10, and given some selection criteria, and then let the humans involved in the process select from the 10 types of patterns, see how well they match the real world, of course, as opposed to 100 million. So these are the types of things that are very easily done now with a lot of the TensorFlow and a lot of the open source free artificial intelligence programs that are being supported by Google and Microsoft and others. It's just a plethora of these types of techniques and many different capabilities, but what we need to do, we need to determine where they fit in the systems theory identification and validation process. But it is definitely an area that can provide great benefit. So, of course, what we enhance, we're going to enhance our capability of a researcher group by using these computational techniques. And we've mostly been talking now about theory and concepts. But most systems engineers and system scientists really don't work on developing theory and concepts. They work on solving problems. So this is to the Warfield's polyloop model. And the polyloop model is a fairly straightforward statement of mostly how things go. You either act on a problem or you act on the process set that creates the problem, or the set of processes, or you act on the theory, right? Or you act on the foundations to the theory. Most people are acting on a problem or a process or act on a process set, right? And this is fine because they're restricted and focused on the customer and solving a problem for the customer. However, from a systems theory and a systems science standpoint, it's possible once there's a range of theories become standardized, we can do quite a bit of matching, pattern matching. We can do quite a bit of automated monitoring and verification and validation in the background. I look at this almost like a computing language lint checker, right? Because really, when you're acting on a problem, you're assuming a common set of theories and a common real-world view, right? You don't check them all. Right? You don't check them. You're assuming those, and just those assumptions then can create problems. So the idea here is to, once we get a little bit more formal idea on the systems theory aspect is to figure out a way in the background of problem solving to actually have a set that goes all the way back to checking and making sure that the theories are not being violated. And this can have some tremendous benefits. So, yeah, the ubiquitous availability of computing resources essentially provides the hardware and software environment necessary to establish and perform this type of automated polyloop modeling. So I believe now we do have the computational capability to do this. It'll be interesting to actually create an architecture that would support it. So, summary and conclusions, the system concepts and theory have great impact, of course. And evaluation and adjustment of these concepts and theories ensure the most relevant components are in use. And so the whole idea is just to standardize this a little bit more, taking some of these concepts that are fairly informally defined, start making them a little more formal, start using some more of the modern techniques and tools available to help improve the efficiency of systems scientists and systems engineers. And with that, we have 9 minutes left. So, are there any questions?
Well, you've kind of produced a very good agenda of things to be considering over the future here. I wonder if we could perhaps structure this agenda in some way at some point using ISM, given that that's which we are talking about amongst ourselves. That would be sort of a request, not to answer that today necessarily. And the other thought, just on your last comments about the polyloop, is what would be a good approach to that from a computational perspective, or procedural. But other than that, yeah, thank you for laying this out. I think there's a lot there to consider as an agenda going forward.
Well, yeah, there's some very straightforward things that can be done here in the poly loop. And of course, it's always kind of one of the things that I thought about, but and that's the idea of decomposition. When we're talking about any system, any real system, let's say in the design mode, right? We're going to have a hierarchical decomposition of the components within that system, right? Though the component decomposition of that system does not match the hierarchical decomposition of the functions of what that system is going to do, then the functional behavior of that system is not linear and additive, right? And so that it has very non-linear responses. However, the weight, if you have a real system, right, when you add up the component weight for space and power, the just standard stuff that goes with engineering, right, those are linear and additive, right? And so in a polyloop model, you could start with the very simple things that says the things that are linear and additive within the structural area, and make sure that they don't, basically violate things that you're concerned about, like, oh, I have a maximum weight for this system. I have maximum power consumption. I have maximum space, things like that. So these are the things where you could start, and then you could go from there. Any other questions? Well, I have one. Where are you these days, Kevin? Are you out of the snow on the East Coast?
I'm back in back in the States, and we had snow again just yesterday.
Oh man!
About the eighth or ninth storm since I've been back.
Oh man! Well, I hope you're doing okay.
Peter, were you suggesting we do like an online ISM to structure an agenda about structural modeling?
Well, exactly in relation to this presentation, yes, that's exactly right.
Well,
would you be interested in doing that? I mean, I think that, the Simpsons have raised a number of areas of further investigation within this particular context, and I think it would be useful to do that.
How would you describe the context?
Well, the structuring of inquiry into even the relationship with mathematics to system science and system sciences. I mean, a couple of times there, Joe mentioned that there's some opportunities for advancing science by better aligning, having a better understanding of the relationship between mathematical approaches and particular system types or system concepts or systems ideas. And so a guide for individuals to follow to help them think about system types or systems that they're studying, and the relative contribution that particular approaches of mathematics could make to their understanding, I think would be possibly helpful.
well, that sounds interesting, Peter. I think Hall's Metasystems methodology lays this out pretty much in detail. I've picked parts of that. Warfield referred to his work quite a bit.
Yeah, we're pretty into this, though, aren't we? I mean, you've referenced Warfield's book Design, which I've got and just pulled off the shelf. I've got Hall's methodology, but for someone coming at this who is not as well versed in all of this, it would be introductory. I'm even thinking about high school students too, to be honest, because when you look at the next generation science standards, cross-cutting concepts, systems and system models are in there. And what we're talking about would be a really good way to, another way to help describe systems and models and problem structuring and the role of mathematics in particular applications, rather than leaping, as in many cases, to, say, a system's dynamics representation of a particular system.
Oh, yeah.
With its strengths and weaknesses. So that's where I'm going, is how would you introduce this to the average 13-year-old to think about systems and math and structuring of problems?
That's an interesting idea, Peter. I think we need to think about that a little bit. So let's see. Would we like to continue a discussion on that later on, next week, 2 weeks from now? What would we like to do?
Yeah, I would. I'm going to give it some thought and talk to my colleagues here and maybe come back with some, at least outline better problem statement from what I've just thought about.
Okay. Well, I'd just like, as we're capping off here, I'd like to mention it. This is the fifth. This, I think, September will be the 5th year of us doing this, and so I would like, if there's any interest this fall in having a face-to-face meeting. There's a local place here that I know that Janet said when they tried to get a house and get people together and talk, they had problems with, reimbursing because of the travel expenses in a house like that. we have a community center that's all wired up. We can have rooms, I think, 18 hours a day, and we're right here near Payne Field, and so there's a lot of places to stay. All of the international travelers and everybody in and out of here to Boeing. So it's a pretty good. And actually, I guess they're flying in and out of Payne Field now. So if people are interested in doing that, I've checked with my local people, and they say July 5th is the date that they're going to open up the rooms for the next registration. So if we want to do something like that, we should probably decide before July 5th so I can get our names in the hat for getting some rooms sometime in the fall. So if not,
okay, so that'd be a good idea. I mean, 5-year review and its application, that might be a very good topic to focus on.
Yeah, well, we printed out all 20 of our technical reports, and they fill a 3-inch binder. So I'm sure there's a book in there somewhere.
I would think so.
All right. Well, with that, so what's 2 weeks from now, Kevin? Are you going to lead the content?
Yes.
Okay. Basically, then we'll have Kevin on for 2 weeks from now, and thanks for joining in. And we'll talk to you in 2 weeks.
Okay. Bye-bye.
Thank you. Bye-bye.
Bye-bye. Thank you.